Hello everyone, I wanted to make this video to show you how to use the TVM solver on the calculator. This function will be very useful for problems in 5.2 covering compound interest, and then problems in 5.4 covering annuities, and 5.5 covering amortized loans. So I'm going to go through and do a couple examples from each of those types of problems, and I'm just going to throw it straight into the TVM solver, but in practice, what I think you should do is actually take the problem and set it up in the formula first, and then jump to the TVM solver to get the final answer. It is important that you understand the formula and you understand the different pieces, but this video is just about the TVM solver, so we're going to jump straight to it. So to get to the TVM solver on your calculator, you're going to press this apps button in the middle, first option finance, and first option TVM solver. There's a bunch of stuff here, and I'm going to run through what each of them represents real quick. So N is the total number of compounding periods. It's the same thing that N represents in the problem. So if your problem is compounded quarterly, N is the total number of quarters. If your problem is compounded monthly, it's the total number of months, and so on. I% is the interest rates. The only catch here is it has to be left as a percent. Typically, when we plug things into the formulas, we convert them to decimals. But for this function, you have to leave it as a percent. PV is your present value or your principal. It's the same thing as P in the formula. PMT is payment. In the formula, it's a capital R. FV is future value. In the formula, it's capital F. And P over Y and C over Y, we're going to keep things simple. We're going to leave these as the same. And they're going to represent the number of times compounded per month, or M in the formula. So for example, if you're compounded monthly, P over Y and C over Y would both be 12. Or if you're compounded quarterly, these would both be 4. And lastly, down here, payment, just make sure that's set to end. We're going to be doing problems where compounding occurs at the end of each month. So when you do have payments, you want to make sure it's set to end, and then you don't have to change it again. And the last thing I'll say real quick is that the formulas that we use these for, out of the PV, PMT, and FV, we're only going to have 2 of the 3. So when you're dealing with compound interest, there are no payments, so you only have present values and future values. When you're dealing with annuities, you don't have present values, so you only have payments and future values. And when you're dealing with amortized loans, you don't have future values, you're only dealing with present values and payments. So out of these 3, 1 will always be 0, and then you're working with the other 2 and the other values in the problem. So let's go ahead and do this first example here on page 22. Alvin purchased a Series 1 U.S. savings bond for $5,000. The bond earns 2.83% interest compounded quarterly and matures in 10 years. How much will the bond be worth in 10 years? It sounds like we're looking for a future value, right? How much will it be worth in 10 years? And notice we have a present value of 5,000. So this is a 5.2 question where there are no payments. So let's go ahead and start from the top though and plug everything in. We are going to hold this for 10 years, but it's compounded quarterly. So it's going to be 4 times a year for 10 years. Obviously that's 40, but I just want to point out you can do arithmetic right here in the TVM solver. I could hit 4 times 10 and enter, and it inputs 40 there, which is nice if you have kind of a, if you're compounded daily for, 15 years, what's 365 times 15? You can just throw it in right there. Interest rate's 2.83%, so as a percent, remember, leave it as a percent, we just plug it in there. We purchased the bond for 5,000, that's our initial investment or our present value. I'm going to enter it as a negative 5,000, and one thing you'll notice from the TVM solver is out of these three pieces, basically one has to be negative and one has to be positive. So the money that we input into the scenario, we're gonna call that a negative value. Now, no matter what, your final answer is always gonna be positive, whatever you record it as, but the way the function works is basically you have negative in, positive out. And so you need to have one of these values negative. So we're gonna enter a negative 5,000 for our present value. There are no payments, so that's 0. We're solving for future value, so we'll leave that alone for now. And then last thing, we're compounded quarterly, so I'm going to set both of these to 4, P over Y and C over Y, 4 times a year. All right, that should be our setup. Let's put our cursor on future value because that's what we're solving for. And if you notice above the enter key in green is solve, so we're going to press alpha and enter, and it solves for the future value. So according to this, if you buy the bond for $5,000, you have that interest rate and you hold it for 10 years. In 10 years, it'll be worth $6,628 and about 92 cents. All right, let's keep moving on. Let's jump to page 28 and do another example. Here we're going to find the time required for $2,000 to double under this scenario. And I just want to point out to you that when you solve for time, typically you have to use logarithms. One of the best things about this, this function on the calculator is it doesn't matter which part you're solving for, it's always the same. You plug in everything else, you alpha enter to solve for the piece you're looking for. You don't have to worry about any of the messy algebra. So let's go ahead and plug everything in. Here we're looking for time, so we're solving for n. You don't have to clear anything out, just kind of leave it what it is, and we'll paste over it when we go to solve for it. The interest rate is 8 though, so we'll plug in an 8 there. We're starting with $2,000, so I'm gonna enter it as a negative 2,000. Still no payments. We want the 2,000 to double, so we're gonna plug in 4,000 for the future value. And we're compounding monthly, so 12 and 12 for those values. This should be our setup, and we're solving for time again. So go up here and press alpha enter on n. The only catch here is these are in months. This is 104 months roughly. And often they want you to answer in years. So technically to go from months to years, we divide by 12. You might think, how can I do that here? Well, don't forget, you can do it literally right here, 104-ish divided by 12. And that'll calculate it. But also you might want to know how to get out of this menu, and just to remind you, above mode you'll see quit, so second mode. It'll get you out of any menu you're stuck in, so that's a good technique to know. So yeah, I'd say about 104 months, or about 8.69 years, something like that. That's how long it would take for 2,000 to double to 4,000. All right, let's jump ahead to page 40. We're going to jump to 5.4 where we talk about annuities. Just to remind you, this only works on compound interest, annuities, and amortized loans. So annuities are just like the kind of savings scenarios we were just looking at, except there's no present value, there's only payments. So you make payments into an account, and then you get some future value out of it. So on this practice problem here on page 40, an employee deposits $100 in a simple ordinary annuity monthly. So that's going to be our payment. So we're going to go to payment, and I'm going to enter a negative 100 because we're losing that money when we invest it. I'm also going to go to present value and zero it out because we have payments instead of a lump sum present value. So there is no present value. Still have 8%. We're still compounded monthly down here. Find the future value. So we're looking for future value if payments are made for 10 years. So the last thing is we're doing it 12 times a month for 10 years. So there's 120 months, 120 for n. Okay, this should be our setup, and we are solving for future value. So we'll go there, we'll press alpha and enter, and that is our future value, about 18,294.60. Keep in mind for the annuities here, that future value is made up of all the payments we made plus all the interest. So we made $100 payments for 10 years already, right? 120 $100 payments. So that's all accounted for here as well in the future value, plus all the interest on top of that. All right, let's jump to page 43. Another annuity problem. This time we're looking for the monthly payments, right? So this problem says you want to have 25,000 in the future in 6 years. The interest rate is 3.25%. How much would you need to put into the account each month, right? So we're looking for a monthly payment. Annuities are often monthly. They don't have to be, but typically we're going to do annuities as monthly. So let's go ahead and start at the top. We are doing this for 6 years each month. So 12 times 6 will give us 72 months. The interest rate is 3.25%. Still no present value. Payment's what we're solving for, so let's leave that alone. And our future value is 25,000. Okay, that's our setup. We're solving for payments, so I'll do alpha enter. It gives us, remember, it gives us a negative value. That's how the formula works. Our answer is going to be a positive $314.94. So that's the monthly payment we would need to make in order to have the 25,000 in 6 years. All right, a couple more examples. Let's jump to amortized loans. Amortized loans, basically the way the amortization formula works is it's going to relate the initial value of the loan, which is P or PV, to the payment you need to pay off the loan in a specific amount of time. That payment would be PMT or capital R in the formula. So there are no future values with these problems because we're not as interested, at least in the first glance, at how much are we going to pay in the future. It's more about if you take out a loan for this much and you have to pay it off in 30 years, what's the monthly payment you need in order to pay it off? Okay, so that just means future value is going to be 0 for all these problems, and we're just going to relate present value to payments. This first example is what we call the present value of an ordinary annuity. which is kind of a weird topic. What we're basically saying is, the annuities, we make monthly payments and we get some future value out. The present value of that annuity is saying, instead of making payments into an annuity, let's say you wanted to make a regular savings account and you wanted to put a lump sum in there and you wanted to end up with the same amount in the future. So that lump sum that you would have to put in is what we call the present value of an ordinary annuity. Basically, it's the lump sum that would get you the same future value as your payments would in your annuity. So basically, given our payments, we're going to find our present value. So given payment, what is P, or given R, what is P? So if we go to the formula, starting at the top, looks like this is, we're making annual payments compounded annually for 25 years. So N is just going to be 25, right? Total number of compounding periods in this case is total number of years. Our interest rate's 8%, so we'll make I percent 8. Present value is what we're looking for, so we're going to leave that alone. But it looks like we're making yearly payments of $90,000. So I'm going to enter it as a negative $90,000 for payments. There are no future values, like we said, and compounding is going to be done yearly. So it's 1 for P over Y and C over Y. All right, this is our setup. We're looking for the present value, so we can do alpha enter on PV. And so what this is saying is you can either make $90,000 payments for 25 years, or you can make a one lump sum investment of about $960,000 and 729 and about 86 cents. If you make that lump sum investment after 25 years versus the 90,000 for 25 years, you're going to end up with the same future value, right? So this is really just kind of comparing two different modes of investment. Do you want to make these payments of $90,000, or what lump sum could we make that would give us the same amount after 25 years? That lump sum is what we call the present value of an annuity, and it would, in this case, be this value. This is not the most straightforward use of this formula. Typically, like we'll see here in 49, typically this is applied to some type of loan, often like a mortgage payment, like a home loan. We're going to do number 49 here, where it says, find the payment necessary to amortize a loan of $25,000 at an interest rate of 8.4% compounded quarterly in 24 quarterly payments. These are often, most of the amortized loan problems are actually monthly, but as we saw a yearly and a quarterly example. And it's the same idea. Really what we're relating is the initial value of the loan, which is $25,000, to the payment we need to pay it off, which is what we're looking for. They tell us 24 quarterly payments, so we're just going to plug in 24 for N. 8.4% is our interest rate. PV this time is the initial value of the loan. That's going to be 25,000. I'm going to enter it as a negative 25,000, and then we'll solve for payments. There is no future value, and our compounding is done quarterly, so these should be 4. All right, this is the setup. So now we're going to find the payment we need in order to pay off this $25,000 loan after 24 quarters. And it looks like that payment would be $1,336 and about 80 cents. All right, we just did 6 quick problems. We did skip plugging it into the formula, which I think is an important skill that you should practice. But at the very least, we didn't have to do any of the algebra. We plugged in the values, we got the answer. And the more familiar we get with this function, I think the happier and the smoother things will go. So hopefully this video gives you a taste of how to apply the TVM solver to a variety of different problems. And thank you all for watching. Let me know if you have any questions, and I'll see you next time.